Welcome everyone to this explainer. Today, we are exploring the invisible bridge that makes our entire modern electrical grid possible. I'm talking, of course, about transformers. Literally without them, the reliable electricity that powers our homes, our hospitals, and the very devices we use every day, it just simply wouldn't exist as we know it.
But before we get into the nuts and bolts of it all, I want you to think about a bit of a paradox. How exactly does electricity jump from one circuit to another without a direct electrical connection? I mean, imagine trying to pour water from one glass to another without the water ever crossing the space between them. Sounds impossible, right? Yet in the electrical world, power transfers across a physical gap every single second of every single day, and the wires literally never even touch. So how is that actually possible?
Well, the answer turns out to be this device, the transformer. By definition, a transformer is a static electrical device that transfers energy between circuits through something called electromagnetic induction. And crucially, it does all this while keeping the frequency exactly the same. Okay, let's dive into this, because electromagnetic induction is the absolute secret mechanism here. It is the invisible bridge we're going to explore today. So here is our roadmap for the explainer. 1. The magic of induction. 2. Faraday's law in action. 3. Inside a transformer. 4. Controlling the voltage. And finally, 5. Powering the modern world. All right, let's kick things off with Section 1, the magic of induction. You see, this incredible feat of electrical engineering relies entirely on one fundamental rule of physics, and that is Faraday's law of electromagnetic induction. It states, and I quote, "Whenever a changing magnetic field links with a conductor, an electromotive force, or EMF, is induced in that conductor." Now, I want to really focus on that word changing. A transformer only works with alternating current, or AC. If you were to push a steady, unchanging direct current through it, absolutely nothing happens across that gap. The magnetic field must constantly be shifting, expanding, and collapsing to actually push the electricity across our invisible bridge. Moving right along to Section 2, Faraday's law in action. Let's see how this builds. The exact math behind Faraday's discovery is represented by the EMF equation. So E equals 4.44 times F times N times phi. Now, don't let the math intimidate you here. It's really just a recipe. E is the voltage we're trying to induce. To get it, we multiply a constant, 4.44, by F, which is the frequency of our alternating current, by N, which is the number of turns or coils of wire we have, and by phi, which is the maximum magnetic flux. That's essentially just the strength and spread of the magnetic field. So if you want a bigger spark across that bridge, you just increase the frequency, coil the wire more times, or pump up that magnetic field. So, how does this whole sequence play out in real time? It happens in 6 very precise steps. First, the AC supply is applied to the primary winding. Second, because it is AC, a changing magnetic field is instantly produced. Third, that magnetic flux travels safely through a solid iron core. Fourth, the shifting, pulsing flux links up with the secondary winding on the completely opposite side. Fifth, thanks to Faraday's law, a voltage is induced right there in that secondary wire. And sixth, your load, whether that's a whole city block or just your kitchen toaster, receives the power. The energy leaped, but the wires never even touched. Let's move on to Section 3, inside a transformer. A transformer is actually a surprisingly elegant machine. It relies on a laminated silicon steel core, and that acts like a superhighway for the magnetic flux, while also keeping energy loss to a minimum. Then you've got your primary winding for the input, your secondary winding for the output, and, this is crucial, a whole lot of insulation to prevent electrical short circuits. In massive industrial transformers, you're also going to find transformer oil acting as a heavy-duty coolant. But notice how insulation is a key component here. The primary and secondary windings are physically completely separated. Literally, the only thing connecting them is that invisible magnetic bridge. Now, what's really fascinating here is how engineers actually arrange these components to handle the magnetic flux. Generally, we see 2 main designs. First, in a core-type transformer, the windings surround the magnetic core. That makes for a really simple construction and super easy cooling, which is perfect for everyday distribution systems. But on the flip side, in a shell-type transformer, the core actually surrounds the windings. This design physically traps the magnetic field, and that provides much better magnetic coupling and lower leakage flux. So it's absolutely ideal for high voltage and highly sensitive electronic applications. All right, Section 4, controlling the voltage. Induction is so much more than just a neat parlor trick.
It actually allows us to manipulate the electricity itself. To control the voltage crossing our invisible bridge, we use what's called the turns ratio. It's the primary voltage divided by the secondary voltage, which equals the primary turns divided by the secondary turns. It is incredibly simple when you think about it. The voltage output depends entirely on the ratio of wire coils on each side. If you change the number of loops, you immediately change the voltage.
And that logic leads us to two main outcomes. A step-up transformer has more turns on the secondary side, which increases the voltage for long-distance travel, like across massive power lines. But a step-down transformer has fewer turns on the secondary side, which drops the voltage down while actually increasing the current. And this step-down process is exactly why you can plug your delicate mobile phone into a 230-volt wall outlet and it doesn't just instantly burst into flames. The transformer stepped that massive energy down to a gentle 12 or 5 volts. Finally, Section 5, powering the modern world. Get this, modern transformers operate at an efficiency of between 95% and 99%. I mean, that is a staggering engineering achievement. It means that when massive amounts of electrical power are translated into a magnetic field, pushed across an air gap, and translated completely back into electricity, almost none of the energy is lost on that invisible bridge.
So the crucial point is, why isn't it 100%? Well, no machine in the universe is completely perfect. We have 4 inescapable energy drains to deal with. Copper loss happens because the wire windings just naturally have electrical resistance. Core loss, sometimes called iron loss, happens due to hysteresis and eddy currents fighting the magnetic field in the steel itself. Stray loss occurs when a tiny bit of that magnetic flux leaks out of our perfect bridge. And dielectric loss happens within the insulation materials themselves. But honestly, even with all that, losing only 1 to 5% of power overall is just incredible.
Now, to meet the wildly different demands of our modern world, this one core principle of induction takes on a lot of different physical forms. Based on the phase, we have single-phase setups for our homes and massive 3-phase ones for giant factories. Based on application, you've got giant power transformers humming at generating stations and much smaller distribution transformers right on your local street. And for specialties, we use isolation transformers in places like hospitals for absolute safety, or highly compact auto transformers to regulate voltage super efficiently in a single winding. The everyday impact of this technology literally cannot be overstated. I mean, why does all this matter? Because transformers are everywhere. They're in the power generation stations producing the current. They're in the tiny adapters charging the laptop you might be using right at this very moment. They ensure safe, isolated power in hospitals, run heavy machinery in huge industrial plants, stabilize the grid for renewable solar and wind systems, and they even power the overhead lines and railway electrification. But hey, a quick word of warning here. While the magnetic bridge itself is totally invisible, the electrical danger is very, very real. Transformers deal with deadly amounts of voltage, so safety absolutely always comes first. Never touch live terminals, ensure absolutely proper grounding, always use insulated tools, wear your personal protective equipment, and never, ever overload the system. We have to respect the physics here. And this brilliantly illustrates how transformers are the true backbone of modern power. They do all the heavy lifting of efficiently shifting voltage up and down while seamlessly maintaining the exact same frequency, all entirely through the miracle of electromagnetic induction. Really, understanding Faraday's law unlocks the secret to our entire global power grid. So I'm going to leave you with this final thought. We've spent this explainer looking at how electromagnetic induction allows us to transfer power without touching inside these metal boxes today. But how might we harness this exact same invisible bridge to power the totally wireless world of tomorrow? Imagine a world where the gap isn't just a fraction of an inch inside a steel core, but across a whole room, or even across a city. The physics is already there, just waiting for us. Thanks so much for learning with